Welcome back. This is lecture 18. So we were discussing about input referred noise of a two-port network, and we took the example of a common source amplifier with only the noise contribution from the transistor in place. So that was the only noisy element in the example that we took. So what we'll do in today's lecture to begin with is to do the input referred noise model of the same network but with another noise source in place. So essentially we'll have two uncorrelated noise sources, and then we'll try to figure out what will be the effective input referred noise model, and then I'll talk about some of the pitfalls that we might need to be aware of. Okay, so as the lecture progresses, hopefully things will become clearer, right? So what is the goal? The goal is, let's say I have a network with a transistor and a resistor. Let's say it's a common source amplifier, and we are only interested in this case the small signal equivalent, right? So essentially this is the incremental ground, and I have a input EI and R connected to it, and I am interested in finding out what is the noise model Vn In for this entire contraption, and I understand that the input impedance is CGS 1 over j omega CGS. Right, I'm interested in finding out what is this if a source is driving my common source amplifier, right? So what is the equivalent noise model that the source is observing? I understand that the source is seeing the impedance of 1 by j omega CGS, but I'm now also interested in finding out what is the equivalent noise model. Okay, so that is the goal. So let's do that. So let's quickly, without spending too much time, let's quickly reuse some of the expressions that we had gotten in the previous lecture. So again, step 1 is what we'll do. Since we are only interested in finding out the noise model, I don't need to take into account the source at all, because the noise model is independent of the source and the source resistance, right? So I'm interested in finding out so this is noisy, right? Here this is also noisy. Okay, so let's call this RL. We have a noisy RL and we have a noisy transistor, and we want to replace this element with some equivalent noise voltage source Vn and some equivalent noise current source In, such that I can replace my noisy transistors with noiseless transistors and noisy resistors with noiseless resistor at the output, right? And how do I know if I am successful in this transformation? I'll be successful only if the total output noise, voltage or current, as it turns out in case of transistor circuits, is easier to deal with currents. So the equivalent short circuit current, let's say IN out, should be identical to to this case. If the IN out in the noisy circuit and the IN out in the noiseless circuit with the equivalent noise sources at the input are identical, then I know the transformation is fine, right? So in order to do that, what I'll essentially do is I'll reverse engineer the process. I'll find out the IN out and then find out from there I will find out equivalent VN and IN. So then the chances of making a mistake is 0, right? So I'll start with the answer and then find out the question essentially. Okay, so let's do that. Now note that in this case there are two noise sources and two uncorrelated noise sources, right? So M1 and let's say this is RL. M1 and RL are uncorrelated noise sources. Okay, so which essentially means that I can deal with the noise contribution from each one of them separately and use superposition, right? That's what I'm going to do. But before doing that, you also need to be careful is VN and IN are not uncorrelated, right? Why? Because VN and IN can both have contributions from M1, from the noise of M1, and I mean I can model, I need VN and IN to model the noise contribution from both M1 and RL, right? So that part of VN and IN which are modeling the noise of M1 will be correlated, and that part of VN by IN which is modeling the noise from RL will be correlated, but these two sets will be uncorrelated. Okay, so that is something we need to keep in mind. So what I'll do, I'll break up this analysis into two parts in which I'm trying to figure out the VN equivalent VN and IN for M1 for the noise contribution of M1, and I'll try to figure out the other parts, that is the equivalent VN and IN for noise contribution of RL. And while I'll treat these two subsets separately, but the individual subsets subcircuits will be used to get the equivalent VN and IN for either of them. Okay. So what happens if I am taking noise contribution from M1 into account only, right? So what is the equivalent noise, or rather, if I am only taking into account the noise contribution from M1 and not from RL, so essentially I know that the M1 noise is IN M1 and the short circuit noise current essentially is IN M1, and it does not have any contribution from RL, right? So the equivalent VN and IN, so I can basically say the VN for M1 is the same thing that I derived in the previous lecture, which is IN M1 over GM, and the equivalent IN, right? So equivalent IN M1. So basically I'm talking about this VN and this IN in this context is equal to J omega C by GM times IN. Okay, fine. Now, so this, what did I do? I only takes noise from M1 into account. Similarly, if I take the noise from RL into account and not take the noise contribution from M1 into account at all, right? So that is case 2. Then what should I get? Nothing changes here. So I mean, you can use the equivalent noise current model or the noise voltage model for the RL, but in this context I would prefer using the noise current model. So this is INRL and this is the INRL that flows out, right? So for this case, your VNM, equivalent noise voltage at the input, VNRL, will be INRL over GM, and basically follow the same steps. You get for the noise current, you get INRL, which is J omega C by GM times IN, right? So now what is the equivalent noise picture then? So the equivalent noise picture becomes, you have a Vn and you have an In, and you have a 1 over J omega C, and you have this input, this R, right? Right? And Vn has two contributors. Vn has Vn. What are the contributors? Vn is VNM1 and VNRL. So VNM1 plus VNRL. Note that VNM1 and VNRL are uncorrelated, right? And similarly, IN has two contributors, and they are INM1 plus INRL, and they are independently uncorrelated, but I know that VNM1 and INM1 are correlated and VNRL and INRL are correlated, right? That's the part that I am trying to impress upon you. Okay, so now if I want to find out the total output noise voltage across the capacitor, right? So I am trying to find out the total output, or essentially I am trying to find out the equivalent power spectral density, right? So for that, first step is to find out the total voltage across the capacitor, or total noise voltage. So let's say I call this VNC, right? So what am I going to do? So to note that this R is also contributing to noise, but that is uncorrelated noise. I am going to treat it separately. Okay? I am trying to figure out what is the noise due to my input, this referred current and voltage sources across the capacitor, right? So to do that, what I will do, I will desensitize everything other than the noise sources of interest, right? While finding out noise, I do not need the help of any input signal source, so I can get rid of that. Okay, and I'm not doing the calculation for the noise from the R, so I will also not use that, right? So the equivalent noise source for the R is not used right now. We are going to use it later. So what will be the equivalent? So now we'll consider to find VNC. What are the steps we are going to follow? Step 1 will be have all the correlated noise sources on and desensitize all other uncorrelated sources, and do it for step 2, do the step 1. So this is step 1, step 2, do step 1 for all uncorrelated noise sources, And step 3, combine the power spectral density from whatever we get from step 1 and step 2 at the output, right? So add PSD, add noise PSD, add VNC to find total noise PSD. Okay, so let's go ahead and do what. So what are we going to do? First, I said that I'll do the noise from R in the end. So let's do the noise from noise contribution from M1, right, in the beginning. So let's do that. So we have this R. So this is VN1. This is VNM1, right? 1. This is INM1, and you have this capacitor, and I'm going to find VNC, but for M1. Okay. Now, important thing to note is that if you go back to the previous lecture, you will see that this model of VNM1 and INM1, since they are correlated, their directions are also important, right? Note that the directions here, this is plus minus, and the current is flowing into the terminal, right? Flowing upwards. So that is important, right? When you are dealing with correlated noise sources, the directions and the positive and the negative signs, right, also become directions, or the polarities also become important. Okay, fine. So now what is VNCM1? So let's use superposition and do one at a time. So if I keep the voltage source on and remove the current source, and removing current source means setting the current source to 0, which means open circuited. So then essentially your VNCM1 becomes Vn, it's a low pass filter, so VNM1 by 1 plus j omega RC, right? And now in the step 2, if I desensitize the voltage source, that is set VNM1 to 0, and use only the current source, then basically the current source flowing into a parallel combinations of R and C. So I will get INM1 times R by 1 plus j omega RC, right? Okay. So now, what is VNM1? Now recall, your VNM1 was INM1 by GM, right? Your VNM1 was INM1 by GM, and INM1 was j omega C over GM times INM1, right? Okay, so let's simply replace those expressions. So this becomes INM1 over GM by 1 plus j omega RC, plus this one becomes, I think I messed up the terminologies. I should not use INM1 here, because there also I'm using INM1 for the input referred, right? So I should use, let me be careful. So I should use INM1 out, right? INM1 out. So this should be INM1 out. Similarly, I should use INRL out. To distinguish that, one is actual output current, and other is a model referred current, right? So in this case, INM1 is not an actual noise current source, it's a modeled one, but the output noise is actually actual noise, it's not a model noise. Okay, so this becomes INM1 out by GM by 1 plus j omega RC. This becomes INM1 out times j omega C by GM times R by 1 plus j omega RC, right? So if I take out INM1 out over GM, so I get BNC M1 to be equal to INM1 over out over GM times 1 plus j omega RC by 1 plus j omega RC. Surprise, surprise, these two cancel. So I get essentially your VNC M1 to be equal to INM1 out over GM. Right? Extremely simplistic expression, but does this make sense? Why should it make sense, or why should it not make sense? So to understand whether it makes sense or not, let's try to figure out what you are actually doing. So we are essentially saying that I have this is the only noise source, this is INM1 out, and I am trying to model I am trying to find out VNC1, equivalent VNC1. So if we have an equivalent VNC1, then your VNC1 times GM should be equal to INM1 out, right? Isn't it? So if I am able to model everything as a voltage source that I have just shown, then your VNC1 times GM should be equal to INM1 out, which essentially means that VNC1. So the only reason we went through this process was to convince you that you can come up with a solution using the very straightforward manner, and also using this model. Now you might think, what's the usage of this model? The usage of this model will be evident later on, when you will see that there are multiple correlated and uncorrelated noise sources which come into play. Okay, and the other part that is important to understand is what we just did here is to find out the equivalent noise voltage at the input of this transistor across the capacitor. But that does not mean you can replace this capacitor with a voltage source, because if you do that, you will not be able to take into account the effect of the other noise sources that precedes this contraption. Okay, so let's complete this thought. Let's complete this noise analysis. So right now what we did, we essentially followed a process, and we found out that the equivalent noise voltage across this capacitor, right? Note that it's an equivalent input referred noise voltage. It's not as if you put a voltmeter at the input of the capacitor, you are going to see this noise voltage, right? This is the mathematical construct that you are going to that we have used to help our analysis simpler. How it is simpler, we will see in the next few minutes. But for the time being, we should keep this in mind. And this SVNC, due to the noise current because of M1 is 4 kT gamma by GM. Similarly, we'll also have a equivalent noise at the input side across the capacitor, right? Due to the resistor, which we have conveniently neglected till now, right? Because of this resistor RL, right? What is the power spectral density of the noise current? SINRL at the output is 4 kT by RL, or 4 kT GL. I'm writing in the form of 4 kT GL because you see that then the analysis is exactly the same as it was using the noise from the MOSFET. So without going through the total calculation, I can simply write the input referred noise voltage spectral density due to RL is 4 kT by GL, right? So okay, so now we have, so what is therefore the total input referred noise across the capacitor is a summation of the two uncorrelated noise spectral densities, which means this is 4 kT times gamma by Gm plus 1 over Gm. Okay. So this is not the full story, because now what did we not use? We did not use the noise from the input resistor, right? That will also contribute to a noise, right? So, but that analysis is quite straightforward, because since I have the resistor, and let's assume this is the noise source which models the voltage noise from the resistor, right? And we have this Vn and In that is not necessary anymore, because I am using superposition. I am only taking into account the noise contribution of the resistor, because the other contributions we have already found, right? So I essentially get this is C. So by the way, this is SVNC due to network, due to M1 and RL, and this is a VNC due to R. Okay, so now we have done this before. So what is SVNC due to R? This is 4 kTr by 1 plus omega squared R squared C squared, right? So essentially, what is the total? So total, simply said, total effective noise PSD referred to the capacitor, or referred at the across the capacitor, is equal to 4 kTr by 1 plus omega square R square C square. So let me use another symbol for that. So let me call this as SVNC now. This is SVNC due to R1 and RL. This is total SVNC. So this is due to R, and the other one is 4 kT gamma by Gm plus 1 over GL. So this is due to M1 and this is due to GL. Okay, so this is the total noise path spectral density. Now, as it turns out, there is a terminology that RF engineers use to characterize the noise performance of a system. Okay, so let me give you the definition first, and then I will try to motivate why this is of some interest. So if this is a total noise, right, and I can split it between the noise that comes from the input source and the noise that is a property of the network, right? So this is the noise from the input, noise due to input source resistance, and this is noise due to network, right? So what is the ratio of the total noise contributed? I mean, what is the ratio of the total noise at the output to the total noise due to due to the source only. And why is that important? So if I simply say that, let me define a parameter called f, which is essentially simply say total noise due to all elements divided by noise due to the source only, right? So what is that in our case? So total noise is SVNC, and noise due to source only is 4kTr by 1 plus omega square r squared c square, right? So I can write the total numerator here as noise due to source only plus noise due to all other elements divided by noise due to source only. So which essentially means this is 1 plus noise due to all other elements divided by noise due to source only. Okay. So this definition is called, this F is essentially the noise factor. Okay. So what is, now it should be quite evident to you why is this noise factor important. So what is the noise factor telling you? The noise factor is telling you that if your network is noiseless, right? If your network is noiseless, then the noise due to all other elements will be 0 and your noise factor will be 1. But if the rest of the network is contributing to substantially higher noise than the noise due to source only, then this noise factor is a measure of how much extra noise your network is contributing to. Okay. So ideally, what do you want the noise factor to be? You would want ideally the noise factor to be equal to 1, right? Because you would want the noise contributed to all other elements to be much smaller than the noise due to source only, right? So ideally, we want noise due to network to be much smaller than noise due to source, right? Why? Because the noise due to source, we cannot do anything about it. It exists. If it's a 50 ohm resistor that comes from the antenna, you cannot do anything about it, right? All we can do is to not make it any worse. If you can satisfy this noise due to network to be much less than noise due to the source, then all you are saying is that I am not degrading the noise performance of the system, right? There is another terminology associated with it, that is basically noise figure, which is nothing but the log scale of noise figure. Log scale of noise factor is often called the noise figure. And if your ideal noise factor is 1, then obviously the ideal noise figure should be 0 dB, right? So that is something that we should be aware of. Okay, so it is never achievable, obviously, because you will never get a transistor or a resistor or which doesn't have any noise. right? But at least we know that there is a metric to characterize the noise performance of the system, and that is through noise figure. Now, the more traditional definition of noise figure, and which is the more accurate definition of noise figure or noise factor, is the following. So, let's say you have a system which is, you have a source. I don't have to make it an antenna. Let's say you have a source which has some input, some resistor, which contributes to noise, and you have a network, right? Some network. Right? So let's assume that the network is noiseless. So if n is noiseless, right, I can find out the output, maybe voltage, maybe current, but if n is noiseless, I can find out the signal to noise ratio at the output, right? If n is noiseless, let the SNR at output be SNR I. Okay, and if n is noisy, let the SNR total, right? So it's including the source, total SNR at output be SNR total, right? So the ratio of SNR total by SNR due to the input only can be expressed as what? So what is the SNR due to the input? The signal. So I can simply say that this is, so input signal power, let's say P in, multiplied by the gain, right? I'm talking about power gain here, multiplied by the gain divided by, right, divided by the noise due to the input, right? Again, multiplied by the gain. By the way, I should write the definition. G is equal to power gain, right? And what is the SNR total? Signal at the output is still P in times G, right? Divided by what is the noise at the output? That is N in times G. N in times G is the noise at the output due to the input source only, plus N due to network, correct? So what do you see? You essentially see this goes, and I get N in times G by N in times G plus noise due to the network, which means that your SNR due to the input only divided by the total SNR is nothing but 1 plus NN by NN times G. So what is NN? So this is total noise. And what is NN times G? This is with noise due to input only. Well, all the other noise sources have been nulled, right? So now what is then SNR in by SNR out? This is exactly the definition of noise factor, is 1 plus noise due to all other elements divided by noise due to the source only, or like basically the total noise total noise divided by the noise contribution of the input only, right? So essentially your noise factor definition boils down to SNR in divided by SNR out, or SNR total. More formally, it is also called SNR in divided by SNR out. right? So also referred to as SNRin over SN. Okay. So what is noise factor for for uh, for the block that we just did? What is the noise factor for the block that we just did? So that's pretty straightforward. So essentially, I know the noise due to the network and I know noise due to the input only. So for the common source amp, the noise factor is nothing but 1 plus 4 kT gamma by Gm plus 1 over Gl divided by 4 kTr by 1 plus omega square r square c squared, which is nothing but 1 plus omega square r squared c squared times gamma by Gm plus Rl. Okay, at very low frequency, this term vanishes, right? You essentially get 1 plus gamma over Gm plus Rl. Now, this also gives you a nice way of understanding how to minimize the noise factor, because now you see that Gm is in your control, RL is in your control, right? Or GL is in your control. So I keep writing in the form of GL so that I do not have to deal with resistances and conductances simultaneously. So what do you need to reduce your noise factor? Clearly, you need to increase your Gm and GL simultaneously, right? So to reduce F, increase Gm and GL, right? But can you increase Gm and GL arbitrarily? Let's say I keep on increasing Gm and don't do anything to GL. Obviously, noise factor will reduce, but do you see any problem? So clearly there will be a problem with the biasing, right? How do you increase Gm? You essentially increase the size or you increase the current. Moment you increase the current, there will be a quiescent drop across the RL and you will end up in trouble, right? So what is the easiest way to go about doing it? So easiest way to go about doing it is to say that, again, this is the oldest technique in the book to reduce noise. If this has a transconductance Gm and this has a conductance GL, all I need to do is copy the same circuit again, maybe twice in this case, right? So copy paste the same circuit and connect them node to node. So I connect this to this, I connect this to that, I connect this to this. So this is GL, this is GM. So what is the effective? Now what is the effective GM? So GM effective is equal to 2 GM and GL effective becomes 2 GL. That clearly reduces the noise factor without changing the transfer function, right? Without changing biasing or anything, right? So again, just like signal to noise ratio that we had talked about earlier, in order to reduce the noise factor, your handle is still the same. You essentially copy the circuit multiple times and put them together node by node in parallel. What is the trade-off? Obviously, the trade-off is the power consumption, because if one of the stacks was consuming I current, 2 stacks will consume twice the I, right? So that is something you should also always keep in mind. But at least we understand that this is consistent with whatever our intuition behind improving the noise performance of a circuit is, right? So the definitions of signal to noise ratio and the definitions of noise factor are not at conflict with each other. That's all it is pointing to. Now the question that you before I stop here, the question that you might want to ask yourself is, while doing all these calculations, I referred everything across the capacitor. will that definition of signal to noise ratio or the noise factor change if I don't refer it to the capacitor but finally at the output? What do you think will happen? Will it change? The question that I'm asking is, you have a network. I referred everything to its input, right? I had a noise source, I had a signal source, I had a noise source. I found out uh, um, some port across which I referred. I did all the calculation, right? What if I had not chosen that port and I had chosen a different port, maybe the output port? In this particular case, take the example of take the example that we have just treated. If we had taken the output port, would the noise factor be any different? Clearly not, because when we are doing all these calculations, we are assuming this is noiseless, right? If your network is noiseless, then the signal to noise ratio as you proceed down the network doesn't change, right? Signal might get attenuated, noise might get attenuated, or your signal might get amplified, or the noise might get amplified, but whatever happens to the signal will also happen to the noise simultaneously, and with exactly the both of them will pass through the same transfer function if the network is noiseless, right? So hence the SNRs do not change as you go through this noiseless network. So which essentially means that you can do your noise figure calculations at the input port, at the output port, it really doesn't matter. You can refer everything to an input and do your noise figure calculation, or you can refer everything to the output and do the noise figure calculation. But you have to be careful when you are doing at the input side. You have to ensure that you have referred it properly. There should not be any residual noise source in the network. Then your calculations will be incorrect. Okay. We'll stop here.